So welcome everybody to today's WISE Zoominar on wave current interaction. We have two very exciting talks that I'm looking forward to. The first is going to be from Dr. Delphine Hypolite from UCLA. We can ask questions in the chat, or I think, Delphine, if you're okay, maybe we can stop if we have questions during, and then we'll have time for questions at the end.
Absolutely.
Great. So without further ado, Delphine, the floor is yours.
Awesome. Going to share my screen. Do you see everything?
Yes, looks great.
Awesome. Okay. Well, good morning, everyone. At least it's morning for me in California. I'm Delphine Hypolite. I'm an assistant researcher at UCLA. I had said that I would talk about non-conservative wave effect in the nearshore on submesoscale, but I slightly changed my mind because I got some recent new result that I found very exciting. So I decided I'm going to talk about that instead, but it's still wave current interaction. The work I'm going to talk about today is done in collaboration with Jim McWilliams, Lionel Romero at the University of Connecticut, Daniel Dawahe, Kaushik Srinivasan, sorry about that, and Roy Barker, who's at the University of Tel Aviv. This is a raw outline of what I'm going to talk about. In the first part, I'm going to talk about simulations that I do with ROMs and how we can take into account wave current interaction in them and how they modify the submesoscale in particular. And we're going to talk about how they can, in some cases, generate Langmuir turbulence. In the second part, and that's the part that is very recent, I'm going to show you some very first preliminary cross-validation of observation with those models, and especially in the context of Langmuir turbulence by the mean of structure function. Okay, so the first part of that talk, we're going to try to just angle the question around what can we learn really with this type of numerical simulation I've been doing. We call them realistic, but they still include a lot of approximation, as you can imagine. And so, which is the part of the physics that we trust, and what are the things that we can learn from that? All right, so wave current interaction. This is a picture that we took at Venice Pier 2 winters ago. It was a really fun day. Waves are known to interact with currents in at least two scenarios. The first is that one, the obvious one, the one that is very popular, especially for surfers, is that wave break when they reach the near shore. They give back momentum to the ocean, they can engender rip currents. And the second scenario, which is also very exciting, at least for someone like me, is that in the wind-driven mixed layer, they can engender Langmuir circulation. And I've put these tiny pictures on the right to show that. So here you can see them because they create those lines of foam that are the result of the convergence of the surface of very elongated counter-rotating vortices. And they are thought to be generated through the Craig-Leibovich instability, which is an instability that comes from the vertical shear of the flow when there's like large waves or large wind. So how can we try to resolve those phenomena in numerical simulation, especially with ROMs? We use a framework that we call wave average. So we leverage an asymptotical theory that basically separate scales from the super small scales, high frequency wave oscillations to the low frequency currents, right? And basically you retain only the leading order modification on the currents that appears as extra forcing terms in the Navier-Stokes equations and material evections, and it allows you to just solve for the currents without solving the phase of the wave. So it's something to think about, because basically it means that in most cases, I don't have per se a surf zone and everything is parameterized, but it allows me to run at pretty high resolution with, atmospheric forcings and realistic wave forcing, the current that are just responding to that. For the wave part, it means though that you have to run a twin simulation with a wave model. Here we've used WaveWash 3, and we've used a new approximation to describe the Stokes drift that actually Lionel has described in a paper from 2021. And the only thing that I'm going to say about that is that we've tried to do a better job than the monochromatic approximation. That is the one that has been used the most widely before that. And the only difference is that we try to better represent mixed sea state when you have both a swell in the water, but also like the tail of the spectrum with some like wind waves, basically like the high frequency part. And so once you have that from your wave ratio simulation, you can just plug it into RUMS. It gives you your vortex force or the pressure correction to set up. And in case you're interested in the nearshore, you're going to have also like to take into account a lot of the dissipative processes, namely the braking, the bottom drag dissipation, but that I'm going to talk about it slightly later. So I've been doing that for a few years now at UCLA, and I've been playing with that box that is a domain in South California. So you can recognize the basin of Los Angeles. You have Point Conception, Point Argeo address right here. And basically each domain has its own resolution. It's color-coded. And I've been nesting down in resolution to reach those two very small but higher resolution domain here. So that's always the price, right? You want to gain in resolution, usually you have to sacrifice some of the size of the domain because those simulations are so costing. But the nice part about those simulations is that they are realistically forced. We have WRF on one side for all the atmospheric components. We have WaveWorth 3 for all the wave components, and then we have the realistic bathymetry, the complex topography of the region, and we pass through the boundary conditions, the realistic tide, all the circulation, the regional circulation, and all the mesoscale. So it's really like a response from all of those phenomena combined together that we're gonna have a look at. At period of time of winter, which is also an interesting period because it usually means that submesoscale dynamic, which is all those currents that are under roughly 1 kilometer of size, will be more active. And also, when you surf in California, you know that you have better swell at that time. And I have been looking on purpose at regions that are particularly well exposed to those big swells of the winter. So we're gonna have like a combined effect that we expect to be particularly enhanced in our simulation. Okay. So in my offshore box, I have no coastline in this one. This is the type of result that you're gonna get. I'm showing here an animation that loops around a big swell event. And it's surface normalized vorticity. So it's a metric that we like when we want to look at submesoscale because it highlights in bright red all the fronts and the vortex and the filaments that are typical of that flow. It's like highly convergent cyclonic structure. So the simulation on the left has all those ingredients that I've been talking about, except the wave current interaction. And you can see that I recover those super nice filaments. They undergo like some instability. And as soon as I take into account waves, all that submesoscale is still present to a certain extent, but it's highly modified by the presence of the waves that is responsible for that very stripy pattern to appear. And those stripes are, and I'm going to try to phrase that as honestly as I can, an hydrostatic attempt of RUMS at that coarse resolution to produce Langmuir circulation. If I'm being cautious here, it's because I've been observing those Langmuir cells at all the resolution past 300 meters and higher in my simulations, and their size downscale every time. So it means that I'm still kind of under resolving them, most likely. Another jump in resolution will be able to like tell us more about that. I have, though, tried with non-hydrostatic capabilities of RUMS, and the behavior seems to be very, very similar. So it gives me a bit more confidence about that. And what it tells us is that most likely, quantitatively speaking, we are not doing a perfect job with them, but we do expect them to be qualitatively right because they do show most of the property of what we know of the Langmuir turbulence. The Langmuir turbulence is interesting because, as you can see, first of all, it clearly interacts with the submesoscales. There's a lot of things that we can analyze, and like how, for instance, like the frontogenesis will be impacted, the life cycle of any fronts and filaments will be impacted by those. But the first thing that I've noticed and I want you to remember with them is that they are associated with extremely large vertical velocities. And it's because, remember, it's those like counter-rotating vortices. And so they're extremely efficient at putting at depth something that is at the surface, but they can also like advex up things that are within the mixed layer and at the bottom of the mixed layer. So they will become a very interesting feature as soon as you're interested in the face of tracers in the ocean. So now if you would like to do some nearshore studies with wave current interaction with RAMs, you have to make sure that you do a good job at reproducing at least those two effects that are associating with the dissipation of the waves, which is basically the wave breaking and the bottom drag dissipation. The bottom drag dissipation is the fact that like when waves arrive near shore, they're gonna like fill the bottom and it can engender those bottom streaming effects. Both those effects, they will be responsible for an addition of momentum, and I'm not talking with a sign here. So basically you can think of that as a stress, and that's how we implemented it in the latest version of RAMs. So breaking will be seen as a stress at the surface, bottom drag dissipation will be seen as a stress at the bottom. And on top of that, you have an additional vertical mixing associated with it. So because we've been trying to use the broadband approach described by Lionel's paper, we had to revisit the implementation of those phenomena as well, because historically they also have been relying on the monochromatic approximation. It has not been an easy task. That used to be what I was planning on talking about today, but I'm not going to go into the details. Instead, I invite you to be on the lookout for a geoscientific model development paper that we're going to put out, and that's going to have all the details, all of those implementation. But it gives extremely exciting new physics near shore with RAMs when you include the waves. So similarly as before, I'm showing on the left a simulation that has all the ingredients that we've been talking about, except the wave current interaction. It's again a normalized vorticity at surface. I'm showing also a couple of isobar to guide the eye. But as soon as I'm including waves, you can recognize again like a Langmuir turbulence going on offshore. But near shore, there's now like the generation of a lot of like new type of alongshore boundary currents. On the west coast of that point, which is the one that is actually perfectly facing the waves. It's not perpendicular, but it's the one that is the most exposed. You have a very small scale rip current pattern that emerge. You can clearly see that all the topographic wake are well enhanced with waves. And because of that, for instance, if you look on the right, you have that eddy that is generated here, and it creates at times those pulse of like a longshore currents. So there is a lot of inner shelf flow spatial variability here. They will for sure modify both the cross shore and the alongshore transport on the shelf. And so it had raised the question of like, okay, this is exciting new physics. We can talk a lot about like all the interaction, all the phenomenology of what's going on, what is responding to what. But if we want to say something about, okay, so let's say I want to follow tracer, I want to follow biogeochemical quantities, how much can I trust those models who don't have a per se surf zone, who are still relying on heavy parameterization, who are maybe double counting some of the effect of the Langmuir turbulence? And so is there a family of observation that we can use to compare to that? And that's not an easy question. But the good news is that it's the second part of my talk. It's not an easy question because inherently the small scales, they are very ephemeral and they are very difficult because of that to track in real life and to measure. But, and Nick was part of that project and maybe many other of you, NASA founded for the last 4 or 5 years, the S-MODE mission, which was targeted to capture submesoscale currents. It has been a great project involving like many institutions, especially in the US. It's multi-platform, so there was people on planes, there were people on boat, people deployed a lot of different types of drifters and buoys. And the goal was to really do that combined effort to try to capture the submesoscale and all the vertical fluxes associated with them and answer a lot of questions associated with them. For that mission in particular, I have produced numerical simulation for the region, which had the purpose to just be like cross-validation numerical simulations. And I was on board that plane, the King Air, who had two instruments. One instrument was just an SST camera, and the other instrument was the Doppler scat. That is, the PI is Ernesto Rodriguez at the JPL. And what's nice about that instrument is that it's capable of saying something about the surface currents. And so I'm going to show and share some of their very preliminary results. And I'm going to try to guide you through the story of my last 3 months, basically. So they've been showing us statistical results, which is a great way to like try to get a sense of like, what did we get? What did we observe statistically over, like, for instance, one deployment or a couple of deployments? What it is really what we're looking at. And so they've been talking in terms of second order structure function. So I'm going to give you like maybe a brief crash test on that because I'm not sure how familiar everyone is with second order structure function. The simple definition is given back here. A structure function, especially if you're looking at a velocity field, is basically the sum of the variances minus twice the autovariance of the field, right? So you can think of that as just a kinetic energy spectra that is slightly smoother. And we like to look at the shape of those curves because it tells us something about the underlying dynamics, meaning that depending on the slope that we see at different scales, it's going to tell us like, is it 3D turbulence? Is it kindly of isotropic? Are we following a Kolmogorov cascade and these type of things? For also like the sake of those comparisons, I'm going to talk about longitudinal and transverse component, which is just a way of redefining the velocity field. When you look at those like 2-point cross correlation, if you redefine the velocity in the longitudinal components, it's just like the parallel component and the perpendicular to that. So it's just for the sake of comparing to those observations. So this is what Ernesto and Alex have been seeing lately with the Doppler scat during those deployments, which is in California offshore San Francisco, and basically as a function of scales, you have those curves. The blue one is the total kinetic energy. The orange and the green are just those two components, transverse and longitudinal. The part that is surprising and that raises our interest to dig a bit deeper is that they are way flatter. They have way shallower slopes than any of the theoretical expectation based on the turbulence theory. And for that, I had that set of simulation that we've designed for the sole purpose of being able to compare to those observations. So it's not exactly the same simulation that I've been showing before, but it's at exactly similar effective resolution as the Doppler scat, and it doesn't contain the wave current interaction at that stage, simply because that was not the direct objective of that mission at that time also. But so if I compute a structure function to compare directly, this is the type of things that I get. Something that is way steeper than what Ernesto and Alex have been observing. And that is actually kind of the theoretical expectation of just, turbulence theory. But so it means that we are not reproducing observation in that case. And so the question is why? There's several possibilities. The first would be, we know the observing with Doppler scat exactly what we think we're observing. So maybe there's some noise, maybe there's some pollutions from atmospheric rolls, but maybe there's some waves as well. And that's the part that I started thinking about. And especially because I've been doing also all those models with wave current interaction, who gave me, as you can imagine, that huge bias to look for waves into it. So I've been starting to do a lot of computation of structure function in the solution that I've been showing you in California with waves. So namely, for instance, this one, the one that is offshore, just like the DSMO deployment, but it's not exactly the same region and it's not exactly at the same time. But again, it's a statistical comparison, so it's still relevant to a certain degree, even though we need to be careful here. But this is what you get. So there's a lot of curves here. The blue one is just the theoretical expectation of classic turbulence theory. The purple one are from my solution without any wave effect at a very low wind time. And as you can see, roughly purple and blue are parallel. I'm having those steep structure functions that are not reproducing the Doppler scat. And I'm going to directly guide your eyes to the green lines, which is the solution that I obtain with within the regime of like very large wind and very large wave. And basically at that time, it's a solution that is completely dominated by Langmuir turbulence. There's Langmuir cells all over the domain. And now I obtain actually a slope that is completely in agreement. Like it's not the same plot, but if I superimpose them, they are very in agreement together. The Doppler scat suggesting that maybe the Doppler scat actually has some Langmuir turbulence measurements or pollution, you can call it the way you want. But it's quite exciting because it also means that now maybe we can interpret both models and observation together. It's also recalling another set of observation that's been done in the Gulf of Mexico, where at very small scales with plates, they have been observing that break in the classic law of the Kolmogorov. And they also attributed that at the time directly to wind wave forcing mechanism. So this is basically it. I'm gonna end here my talk. I just recall like the main conclusion of what I've been talking about. The takeaway message that I really would like you to take is wave matters depending on the region of the world you're looking at and at the time you're looking at. So please take them into account and or keep track of them because they can make a huge difference and help you interpret your results. Thanks, and I'll take questions.
Thanks, Delphine. That was great. Everyone's giving you a virtual round of applause here. Give you a second to catch your breath. And while you do that, are there any questions? Henrik.
Hi, a beautiful piece of work. Love what you're showing. I have one little technical question. You were talking about wave breaking and bottom friction, creating mixing in ROMs, if I have correctly, right? So
Yes.
Is that, in terms of the bottom friction part, is that done through modification of the mean roughness or drag, or how is that done in ROMs?
So we do modify the drag, effectively. We modified both the drag, we modified slightly the criterion to find the thickness of the bottom boundary layer as well, because we want ROMs to consider that the bottom streaming, basically, as part of the current at the time.
Okay, so that is similar to like the Christopherson and Johnson approach from like 30 years ago or something like that?
It is similar. The only difference is that we are trying every time that it used to have a monochromatic expression in it, we've been trying to replace it by a broadband approach. That's the main difference.
Yeah, yeah. I used to have that in WaveWatch at some time way back. I'll yield the floor to see if anybody else has a question because I have another one.
Yeah, let's see if anybody else wants to jump in quick, and if not, we'll come back. Ah, John.
Hey, great talk. I learned a lot. We've been using a similar kind of version of ROMs coupled with Swan and WaveWatch 3, and we've put in UC's wave current vortex force formulation in there as well. Are you, so you're only taking the output from WaveWatch 3 to drive ROMs? Are you, so you don't have any current effects back to the waves? Is that right?
That's correct. That's something that I would really love to do. That is more challenging than we would be hoping for. And when I say we, it's basically Lionel also is actively working on that. We had this idea of using the Aiosis coupler, where basically, you know, you plug everything together. We thought it would be more straightforward than apparently it is for some reason. But that's something that I would love to just dedicate time to it and just do it, because that would be the next step. We know that there's like, so I'm showing only the effects of waves on currents. We also know that there's current effect on waves. The goal would be to have both consistently together.
Yeah, I mean, we have that. We've been using that. So if you're interested, or the group is interested, we've been doing that for quite some time. So more than happy
Extremely interesting.
to share that out. And yeah, I'd be interested to know about your Stokes too, because we've updated the way, instead of using the bulk parameters, we use
So how many variables, if I may ask, do you share between the codes?
what I can do is I can send you some information after this, and that might just be best to save time. But yeah,
I would appreciate that.
Yeah, okay, sure. Yeah, and I'd be interested in your Stokes information too, because we've updated that as well. So I think we need to use more information from these wave models. And I think Hendrik will agree on that just using these bulk parameters from the wave models are horrible, that we need to use more of the full spectrum information. Right?
Yeah, not just that, also the depth variability of it.
Yes.
Lots of stuff. There's lots of stuff we can do still. Yeah.
Thank you.
Very happy to chat anytime.
Sure.
We still have some time, so
Okay,
Hendrik,
I
go
have
ahead and
a
ask.
sort of far left field question, or more of an observation. So, more going back to historical and indigenous knowledge and things like that. I used to be a sailing teacher and a professional waterman before I became a wave modeler. And so I've been using the Beaufort scale for estimating wind speeds. And so that goes back to 1805. And in the Beaufort scale, figuring out whether you go from Beaufort 6 to Beaufort 7, you're looking for the foam streaks on the water they start creating. And so as we were understanding more and more over the last 200 years of things like Langmuir, people often say that these foam streaks are directly related to Langmuir circulation too. And so, first of all, it's kind of fun to sort of link that back 220 years to what Admiral Beaufort did. The other one is that it may be interesting, if you have time or interest in that, to actually link what you're doing to foam and whitecap observations, if you can make them or not, and whether or not these at least the scale of what you find in ROMs with ROMs driven by WaveWatch are consistent with what you see with the separation between foam streaks in general, if you can see them, and also of course the thing that would be interesting, feeding it back into the visual observation techniques from the Beaufort scale, is that that really links it just to wind speed, with the assumption that could be valid if it's really the young waves that and the actual wind speeds that are doing that. But it could be really interesting, a little side study on what you're doing to see if these streaks are really fully Langmuir associated or not, if they're wind-sea associated or not, and or if they are associated with onset of large-scale breaking in waves. So there's lots of other stuff going back 220 years.
Yeah, that sounds really cool. I would be very happy to explore that. Don't hesitate to contact me, and we can look it up together. I was trying to give a sense of that. So in the simulations that I have as of now, we very much suspect that we still under resolve the Langmuir circulation, because their size, the grid space, the horizontal spacing between the cells is still resolution dependent. So we need to just go to even higher resolution, probably get rid of the KPP formulation altogether, to see what the code does by itself, and get rid also of any double counting potential effects. So like when you look at big waves, they usually also have those lines onto them, and just because I found them fascinating, I've been questioning myself also, like, is this something that is also Langmuir-like? One of the things that I found interesting that those structure function reveals is that the Langmuir turbulence, so if I can go back, oh no, sorry, well, it doesn't matter here. So for instance, if I go back here, One of the results that is interesting that those things suggest is that linear turbulence is not active at one scale. It changes the slope at several scales. So we can have visible lines reflecting the presence of some structure of some specific scales, and yet still smaller scales being impacted by that. Meaning that, like, I would suspect that there's this thing that we can see by eyes. There's something that we can maybe not see directly by eyes because they're slightly larger. I'm just very intrigued. I would love to explore that. So
yeah, along that
contact
same lines, I mean,
Sure.
the question that has not been asked very much either with these foam streaks is whether it's the Langmuir mean flow that reorganizes the existing foam, or that there's actually turbulence generated that keeps the foam alive longer or not. So there's all kinds of other physical questions that can be asked there too still. It's called job security.
There's a lot going on here that's super interesting, but let's thank Delphine again so we can move on to the next speaker, and maybe
thank you,
Jan,
everyone.
if you want to load up your screen here.
Yes. Can you now see my screen?
Okay, now I can, and it's not in full screen yet.
Yeah.
It's not in full screen yet.
Okay. Takes a bit time.
There it is. So we have our next speaker now, Professor Jan Lee, who's visiting us from University of Bergen. So Jan, the floor is yours.
Yeah. Thank you, Nick. For today's talk, I would like to first thank my contributing authors because of their so they contributed to this research contents. And so today the talk is composed of 4 parts. I will briefly start with introduction, and thanks to Delphine. So then it really makes my life easier. So some parts I could basically just skip. And I will briefly also introduce a little methodology I use. So different from Delphine's talk, I focus more on analytical developments, and I will highlight novel physics from this talk, and I will provide a brief summary. So today my talk is associated with a system of surface waves atop a vertically sheared current. So this system is composed of 2 parts, basically 2 flows, which differ from each other because of their different physical features. Surface waves primarily dominated by surface gravity and also surface tension, and vertically sheared current, which can be represented wind drifts, for instance, ocean circulation currents. So this system especially can be used for a naturally generated phenomenon. For instance, extremely large wave events, which have been fascinated a few researchers in the last few decades. And also, wave current interaction can also be very dangerous to offshore, especially maritime activities, because they sometimes can cause very unfortunate events. And also, this is also system can be used to, for instance, understand AOC interaction and how the upper ocean interacts with atmosphere and also deeper ocean. I also decided to include this amazing phenomenon, Langmuir circulation. So thanks to Delphine, so I do not really have to go through this. So now I'm going to introduce a little bit of methodology that we used. So basically, we use analytical approximations to describe the waves atop a sheared current. So this means the following: we consider a depth-dependent current which has a magnitude and also the direction which vary with the depth, and its velocity orientation will be in the horizontal plane. And in addition to the sheared current, which will be considered in the absence of surface waves, we in addition superpose surface waves which can be modified by the presence of a vertical shear current. So this means this system can be described by the continuity and Euler momentum equations for incompressible and in viscid flows, So these two equations, when you're looking at them, it actually means that we already neglected the terms which describe the background velocity, the background current only, because we made the assumption that the velocity profile of the sheared current has a negligible change of the form in the horizontal plane within a few wavelengths or periods. And also the system includes two especially boundary conditions on the still water surface and also on the seabed, so which we use a free slip seabed boundary condition. So this means the system is composed of or described by a set of nonlinear equations, which is very difficult to solve. So we basically use standard perturbation approaches to find approximate solutions to the boundary value problem, as I described before. So I will not go through in detail. So basically, we could express the unknowns in terms of power series in a small scaling parameter. And here we used wave stiffness as our small scaling parameter. And after this expression, we can inserting the approximate solutions to the boundary value problem I introduced before. And this allows us to collecting the same order in this small scaling parameter, and we obtain the boundary value problems in sequence from the lowest order to higher orders. So using different orders and also the boundary value problem allows us to obtain the solutions in different orders and also demonstrate the physics according to different orders in the small scaling parameter. So today the focus is not to focus on the linear phenomenon. So the normal physics demonstrated in the following will focus on third order and also second order wave stiffness. And starting with the second order, so we're going to now first take a look at the Stokes drift velocity induced by monochromatic waves in the presence of a vertically sheared current. So Stokes drift velocity, as Delphine introduced, has been especially used in ocean circulations to represent the driving force due to the surface waves. And especially in the presence of a shear current, we will see in the following the Stokes drift velocity behaves slightly different. So now the setup is like this. We will have a prescribed vertically sheared current, which is represented by an exponential shear profile, so which we assume is given. And also we have angle, which describes the current propagation direction and also the wave propagation direction. So here we use the theta to denote the angle between the current propagation and wave propagation. So now we're going to take a look at the results, which show basically the Stokes drift velocity in 2 dimensions. So 2D means that the current is either following or opposing the wave propagation, and we focus only on 2-dimensional waves. So here plots the monochromatic waves induced the Stokes drift, varying with the water depth, especially the panel on the left, which shows the Stokes drift velocity. And also the panel in the middle shows the particle trajectories computed from analytical solutions. So now, when we especially look at the left panel, and the black line shows the Stokes drift velocity in the absence of current, which means it's basically the classic Stokes drift velocity. So then Stokes drift velocity decreases its magnitude exponentially with water depth. But here, if you look at the blue line here, we will see that especially the Stokes drift, because of the presence of a shear current, you will see the magnitude of the Stokes drift have a non-monotonic dependence on water depth. So this was not reported before. And if we compare the 2D waves and 3D waves, which means now we allow the current propagating an angle oblique to the wave propagation. So in addition to blue line, now we focus on the red line here. So what is the red line? So red line again plots the Stokes drift velocity vary with the water depth. However, the red line is the angle orthogonal to the wave propagation. So this means Now, the Stokes drift does not only have a component in the same direction as the wave propagation, but because of the current making angle to the wave propagation, now we have a non-vanishing Stokes drift luminosity orthogonal to the wave propagation. So the Stokes drift luminosity is one of the quadratic feature of surface waves. And now we're going to take a look at other quadratic features which are corresponding to the forcing of second order waves. And now we consider a scenario where we have a focus wave group, which we assume linear focus at time and also space. And we now using the same exponential shear current. And we will especially vary the angle of current propagation to the wave propagation. And then we take a look at what happens of the wave kinematics because of the second order wave generation. So the second order waves, we understand there are two particular components, which are the second harmonic waves and also the mean waves. So we first take a look at what happens with the second harmonic waves and the introduced horizontal luminosity. So now we're especially focusing on what happens below the group crest and also at focal time and also position. So now here you can see that it especially plots the horizontal luminosity, the Eulerian horizontal luminosity induced by the second harmonic waves varying with water depths. And here, especially when you look at the black dashed line, it corresponds to the case in the absence of current. Because we understand for deeper water waves, the horizontal luminosity should vanish in absence of current, but in the presence of a shear current, you can also see significantly, basically from vanishing to non-vanishing luminosity components along the water depths. So this is the second harmonic waves. And also if we take a look at the main component, and also again, we are looking at only the horizontal luminosity induced by the second order mean waves. So now compared with the case in absence of current, so the absence of current is shown with the dashed black line. So then you can also see this particular, especially the purple one, which shows where the current is propagating in the same direction as the wave propagation. You can also again see this non-monotonic behavior of the magnitude. So especially this with luminosity have far-reaching impacts in the following analysis that I'm going to introduce, which focus on especially the third order effects. So now we're going to take a look at the third order. We consider especially waves up to the third order because this allows us to understand the energy transfers between different waves. We especially described a shear current modified nonlinear Schrödinger equation, which is shown on this slide. So there are a few terms which are the same as the case in the absence of shear current. Here, I would like to highlight especially three components which are considered as a contribution from different depth weighted flows. The first component is the Stokes drift, which we have already known, which can be considered in absence of current, and also the Eulerian return flow, which propagates opposing to the wave group luminosity. And also this was first derived by Dieser. And the third component is what we called a wave correlated shear flow, which especially requires the presence of both irrotational wave induced motions and the rotational flow motions because of vertically sheared current. So if we don't have vertically sheared current, then this component will become zero. So with the help with this newly derived equation, then it allows us to do some instability analysis of Stokes waves. And so now the setup is that we are assuming we have a carrier wave component with a small wave stiffness, and we are using small perturbations in both amplitude and phase. We're especially considering the perturbations in using two sidebands in both the direction, in the same direction as the wave propagation, and also in the direction orthogonal to the wave propagation. So the sidebands in the wave number, and we can also consider the sideband in wave frequency as well. So using the linear stability analysis allows us to find under what the conditions instability occur. So basically, when we have an imaginary sideband in wave frequency, then we can determine whether or not wave amplitude would grow or dissipate. So focusing on the case where the waves would grow, which means that we can identify a region of instability, where so now I plotted a few panels with the horizontal axis being the bandwidth in the direction the same as the carrier wave propagation, and the vertical axis is the bandwidth in wave number in the direction orthogonal to the wave propagation. So there are many panels ranging from A to G. We understand if we have a given wave stiffness in the absence of the shear current, we will only predict one particular instability region. But those from A to G is because of the different magnitude of vertically sheared current, which I will introduce at the following. So especially when we're describing the region of instability as given with this inequity, so this inequity delta is composed through bandwidth, denoted or included in this LR term, and the delta X corresponds to the bandwidth in the direction of the wave propagation. And also the Stokes drift, which you can actually consider in this particular equation being unity. And in addition, as I mentioned before, so in this particular scenario, we also have a Unarian return flow, which has a sign of has a negative sign, but its magnitude is quite small and proportional to the bandwidth. And in addition, we have a term which is called wave correlated sheared flow. So because of the third term, we could find that when gamma B is smaller than -1, we could have the suppression of modulation instability. And when gamma B is larger than 0, so this will lead to enhanced modulation instability. And gamma B being a magnitude of -1 means this is the same magnitude of Stokes drift, which means it's the second order in wave stiffness. So this was exactly the one that I mentioned before for the second order mean wave flows. So then this term can be used to represent the effects of the second order mean waves especially. So this suppression of the modulation stability was already actually measured last year, led by Nick Pizzo, who actually found for especially the case when you have a shear current which has the same magnitude as the Stokes drift, and then the modulation stability can be suppressed, and when the shear current is opposing the wave group. So one interesting phenomenon I found is that for this particular system, so I found it actually very interesting to point out. So this system is the same as when we use the system to predict the Lamier circulation, where the Lamier circulation was found to be can be predicted by the so-called Craig-Labouche type 2 instability, which involves the Stokes drift velocity and also a background shear flow. And instability criteria also involves basically the sign of the product of the background shear current and also the Stokes drift shear. And this means that using the same system, we could have instability for extremely large wave events and meanwhile also Lamier circulation. So which of the two would dominate in realistic scenarios? So this is a question that we don't know. However, a question that we can pose is that, so from this two instability analysis, we understand energy transfers can be done between waves and also between wave and current interaction. However, if this would be from waves to current or from current to waves, so this would be a question that needs to be further investigated. And also, it's interesting to point out that these two instability phenomenon, they have similar time scales, because we can do similar analysis and then find these two would be more or less the same scale. So from observational point of view, when we are doing observations, so that we could also basically use the same time scale and trying to report these two interesting phenomenon and trying to see which one would be dominant if in case that if they indeed are somehow correlated or if they are actually competing with each other. So all the previous physics that I reported today are associated with one particular question, which is, are the wave average flow equations sufficient to predict wave current interaction? So my answer is that in order to find some of the previous novel physics that reported today, so that my answer to this question is no, because this basically requires, especially the phenomena that I reported at the third order, so this especially requires wave phase resolved features included in the equations, and this highlights the need of coupling the two sets of equations involving wave averaged and also wave phase resolved equations. So now I end my talk with a brief summary. The summary is like this. So basically a few mathematical models were developed for understanding how surface waves and water shear current interact with each other. And also a few novel physics were reported because of the effect of water shear current on nonlinear waves. And at the end, I would like to highlight that this need to couple with phase resolved and also averaged flow equations. That's all for today. Thank you very much.
Thanks, Jan. That was an excellent talk. So we have a few minutes for questions. Just raise your hand or you can just ask. So this Stokes drift you're finding that's orthogonal to the main current, does that mean if the groups are finite, you're also driving a return flow transverse to the direction of wave propagation?
So orthogonal would be the Stokes drift, but we will still have the Eulerian return flow, which may not be return, but will be following the wave propagation.
Okay.
Really, yeah.
Thanks. Looks like Paul's got a question. Sorry, I can't hear you at least. I don't know if anybody else can.
Can you hear me now?
Yes.
Oh, thank you. Yeah, Paul Bale from TU Delft. Thanks. I just have a question regarding the Stokes drift as well. I guess my question is twofold. The first one is, in your example, you took the current in the direction of the wave propagation, right? Do you have an idea what's happening if the current is opposed to the wave propagation? And the second part of the question will be, do you have like a magnitude? So what's the magnitude of the current needed to have this effect, or what is basically the magnitude in which it doesn't have an effect?
Well, actually, we have done both for the cases current following and also opposing. So I did not use the example for waves opposing currents because they can make a difference to the Stokes drift when also compared with the case in absence of current, but it's not as significant as what I show in the example. And also the magnitude of the current that I used, if I remember correctly, I think the current that I used is an exponential shear current profile. And if I remember correctly, the magnitude of the velocity of the surface will be close to, I think, 0.8 meter per second, but I need to check in detail.
So, but okay, but how does it relate this magnitude to the magnitude of the Stokes drift at the surface? I
Yes,
guess
they
I'm more
are
interested in
actually,
the
if
in the
you look at the
relative
sorry,
magnitude.
I will just go back because
thank you.
everything were plotted in a non-dimensional manner.
Yeah, yeah.
Yeah, so if you take a look at this 2D case, and then the black line basically shows the classical result, so magnitude 1 from the surface, and then the Stokes drift now you see, so this particular case is 30% of the classical result.
Yeah, so the Stokes drift will be 30%, but the current, your current field, so the magnitude of your current relative to the magnitude of the Stokes drift at the surface, do you have an idea of the ratio?
That I did not know because we did not compare the magnitude of the current with the Stokes drift, because the Stokes drift has to be the second order in wave stiffness. So all were actually plotted against the second order in wave stiffness divided by epsilon squared. So I would say it really depends on what would be the wave stiffness that we're talking about.
Yes, yeah, of course. Okay, thank you very much.
Great. Do we have any other questions? Okay, well, if not, let's thank Jan one more time and also Delphine, both of our speakers today.
Thank you.
This is really fun. And I hope to see some of you in a month in Corsica. And I think if not, we're going to be having a Zoominar again in May. So we'll see you there. Thank you, everybody.